Welcome to AI Paper Podcasts. We dive into the latest research and break it down so you can actually use it. Today, we're looking at something pretty fundamental in generative AI and engineering. Can LLMs go beyond just, writing code snippets or generating static 3D models? Can they actually design complex working machines from the ground up?
Yeah, it's a huge leap, right? Moving from just describing something to actually building something functional. And this paper suggests, well, yes, sort of, but only if you give the LLM the right environment and, crucially, the right language to think in. They developed this interactive environment called BesiegeField. It's actually adapted from the game Besiege.
Oh, the physics sandbox game.
Exactly. So it comes with standardized mechanical parts, gears, wheels, logs, motors, and a pretty realistic physics simulation baked right in.
Okay, so the environment is set.
Yeah.
And the approach is agentic.
Right. Think of LLM agents being given a box of these parts and a goal, like build a car that travels the furthest, or design a catapult that can launch something heavy, high, and far. The challenge is for the AI to figure out how to put these parts together in space, the composition, and make sure it performs the function. And then it has to translate that design into structured code.
And you mentioned the language was key. What was the breakthrough there?
This is really the core technical point. They found that standard ways of representing 3D objects, like using global coordinates for everything, just didn't work well. The success really hinged on using a specific construction tree representation. It basically describes how parts connect to each other, not just where they are in space.
Like Lego instructions instead of GPS coordinates for each brick.
That's a great analogy. That structure, plus a multi-agent setup where different AIs critique and refine designs, and then this special fine-tuning technique called reinforcement learning with verifiable rewards, or RLVR, that whole combination is what unlocked the performance.
And the performance did improve significantly.
Oh, yeah. The best models, after all this fine-tuning, weren't just making valid machines more often, they were making better ones. The max score for the Catapult task hit 7.14, and the CarMax score reached 45.72. That's a huge jump from where they started.
Okay, definitely sounds like something we need to unpack. Let's get into it, how they built this sandbox, why that construction tree was so essential, and the whole agent workflow they used to get these LLMs thinking like engineers.
Right. But first, let's appreciate just how hard this problem is. Machine design isn't just about shape. It's about how compositionality, the way parts fit together, enables functionality, what the machine actually does under physical forces. These two things are totally intertwined.
I see. So you can't just think about the parts in isolation. The way you connect a gear and a motor completely changes whether you get, say, a winch or a spinning wheel. Same parts, different assembly, totally different function.
Precisely. So the core task they formalized for the LLM is this. Given these standard parts and a specific goal defined by a reward function, can the AI discover different ways to assemble these parts spatially? And critically, can it express these assemblies as structured code-defining part types, their relative placements, how they articulate in a way that maximizes that reward?
And there's a real-world motivation behind this, isn't there? Tackling issues in current engineering.
Definitely. Think about modern engineering pipelines. You end up with vast libraries of blueprints. But reusing old designs can be tricky. They might be siloed, or the crucial how-to knowledge just gets lost over time. An automated system could potentially help manage that complexity, maybe even to discover new design principles.
But it needs to be more than just a pattern matcher, right? It needs to explore.
Exactly. It has to be agentic. It needs to navigate this incredibly vast space of possible designs, not just replicate things it's seen before. Now, to make this manageable, the researchers smartly narrowed the scope. They focused specifically on compositional machine design, meaning they focused on the assembly of parts, the static geometry, and how that assembly behaves under physics simulation. They deliberately left out things like choosing specific materials or worrying about manufacturing tolerances for now, but they kept the core challenge, reasoning about spatial arrangement and physical behavior together.
Okay, let's talk about that sandbox BesiegeField. Adapting a game sounds like a clever shortcut.
It really was. Besiege already had a robust physics engine designed for exactly this kind of mechanical simulation vehicles, catapults, weird contraptions. Plus, it could handle custom environments, terrains, obstacles, external forces like wind. It gave them a ready-made, quite sophisticated testing ground.
And the parts library, you mentioned they standardized it.
Right. The original game has almost 80 block types. They narrowed it down to 27 key ones relevant for classic mechanical systems, things involving levers, trusses, rotation. So you have your basic structural pieces. logs, smaller wooden blocks, and importantly, ballast blocks, which are just heavy weights for counterbalancing.
The passive stuff. What about the active components?
Yeah, then you have the parts that do things. There's a rotating block, basically a motor that generates torque, powered wheels, obviously, steering hinges to allow parts to pivot for control, and springs for storing and releasing energy. They also included special objects like a boulder to be thrown and a container to hold it initially.
And how does the AI actually build with these?
It's sequential. You start with a root block, and then each new block attaches to one of the available flat surfaces or faces of an existing block. This naturally builds up that relational structure we talk about, the construction tree, or technically a directed acyclic graph, DAGG. It's very much like snapping pieces together, where each placement depends on the previous one.
Okay, so the environment is set up. What were the specific tasks they tested the LLMs on? You mentioned a car and a catapult.
Exactly. 2 core tasks to test different aspects. The car task was straightforward. Build something that can drive along tracks. The reward was simply the maximum distance it traveled. Pure locomotion.
Simple enough, but the catapult sounds trickier.
Much trickier. Especially the reward. The goal was to launch that boulder as far as possible. But the reward function, R is valid S performance, had some important details. The performance part wasn't just distance. It was the product of the maximum height the boulder reached and the maximum horizontal distance it traveled.
Ah, okay. So you couldn't just build something that, rolls the boulder really far horizontally without actually launching it, or something that pops it straight up but doesn't go anywhere?
Precisely. Multiplying height and distance forces the AI to find a solution that achieves a proper trajectory, a real throw. And that is barrel part added another constraint. The boulder's maximum height had to be over 3 meters. If it wasn't a significant launch, the entire score was 0, even if it rolled far.
That's a clever way to enforce the spirit of the task, penalizing cheat solutions.
Exactly. It forces the LLM to grapple with concepts like energy storage, release, and parabolic arcs. Beyond the main score, they also tracked other things. The rate of producing valid design files, the rate of producing spatially valid machines, no parts colliding with each other, and the mean-max scores across attempts.
Let's pivot to that data representation issue. You said it was crucial. Why did the standard approach, using global coordinates and XML, fail so badly?
Think about describing a complex machine by just listing the absolute XYZ position and the 3D rotation for every single block, completely independently. That's the global position-based representation did. It's very verbose. But the main problem is it contains 0 information about how the blocks are connected or related structurally.
So the LLM just gets a huge list of numbers and has to somehow infer the entire structure and all the joints and attachments purely from those coordinates.
Exactly. If you move one block, you might have to manually update the absolute coordinates of dozens of others to maintain the structure. The LLM has no explicit clues about this block is attached to that block's front face. It's an incredibly difficult inference task.
It's like trying to understand how a car engine works by only looking at a list of the 3D coordinates of every single atom inside it.
Right. You lose all the meaningful structure. That's why the construction tree representation was the breakthrough.
The Lego instructions approach?
Precisely. It's a much more compact JSON format, and it explicitly encodes the assembly logic. For each block, it basically says, I am attached to this parent block ID, specifically on its face number X. It focuses entirely on those pairwise relative attachments. That structural information is what LLMs seem to need to reason effectively about how assemblies work.
Okay, so the representation is key. But designing something complex like a catapult isn't usually a one-shot deal. How did they handle the iterative nature of design?
They used a multi-agent workflow. They found a single LLM agent trying to generate a perfect design from scratch. Rarely worked well. So they set up a kind of collaborative loop. You had a designer agent that would take the requirements and produce an initial draft, a first attempt.
Then what?
That draft goes to a refiner agent. Think of it as a self-critic or a peer reviewer. It evaluates the draft against the requirements and physical principles, identifies potential flaws, and suggests specific revisions. Like, this support beam looks weak. Maybe add a brace here.
And the final piece is checking if it actually works in the physics world.
Exactly. That's the job of the environment querier. This agent takes the current design, runs it through the BesiegeField physics simulation, and reports back the results. It summarizes what happened. Did it break? How far did the car go? What was the catapult's trajectory? This real-world feedback is critical for grounding the refinement process.
They also mentioned using hierarchical construction, like a lead designer and specialist builders.
Yeah, that was another layer. Sometimes a meta designer agent would first break down the high-level goal, build a catapult, into subcomponents. Needs a base frame, needs a throwing mechanism, needs a power source. Then, different builder agents could potentially work on those subproblems more effectively. They found this tended to lead to more consistent results, lower variance in the scores.
It's interesting, though, the paper notes that even with very powerful models like Gemini 2.5 Pro or OpenAI's O3, they still saw specific recurring failure patterns. What does that tell us about the difficulty here?
It tells us that geometric and physical reasoning is still really challenging for these models, even best ones. Structural imbalance was a big one. Agents would constantly design things like tall, skinny catapult bases that would just collapse under the load of the throwing arm or the boulder. They understood tall, but not stable. Incorrect orientation was common too. You'd see a rotating block, the motor, placed so it would swing the catapult arm sideways instead of pitching it upwards for a throw. The agent knew it needed a motor, but didn't grasp the required axis of rotation for the task. And precision mattered hugely. Sometimes the overall design concept was okay, but a slight error in positioning a critical part like the container holding the boulder would cause the simulation to fail because the physics couldn't execute cleanly.
And there was that really striking example of a cognitive error where the LLM completely misunderstood the physics involved, the rubber band case.
Ah, yes, that was fascinating. The agent added rubber bands to his catapult design. In its internal thought process or chain of thought reasoning, it justified this by saying the bands would help stabilize the structure.
But that's not really what high-tension rubber bands usually do in that context, is it?
Not at all. When the environment query simulated it, the immense contractile force of those rubber bands instantly tore the support tower apart. The simulation log showed catastrophic failure at like 0.4 seconds. The LLM had the concept rubber band linked to tension, maybe even stability in some context, but it failed utterly to predict the magnitude and direction of the force in that specific mechanical setup. A huge gap between symbolic association and physical reality.
So to bridge that gap and really push the performance, they needed more than just this agentic loop. They needed dedicated training.
Correct. They implemented a two-stage training pipeline. First was cold start fine-tuning. They took a base model, Qwen 2.5 Fort Me, and pre-trained it on a data set of about 10,000 machine designs paired with chain of thought explanations. These examples were actually generated by a more powerful model, Gemini 2.5 Pro.
So bootstrapping the smaller model with knowledge distilled from a larger one.
Exactly, giving it a strong initial grounding in how to structure designs and reason about them based on good examples. But pre-training alone wasn't enough to maximize performance in the interactive environment.
Which is where the reinforcement learning comes in.
Right. Stage 2 was reinforcement learning with verifiable rewards, RLVR, using an algorithm called GRPO. Here, the agent learns directly by trying things in BesiegeField, getting the reward signal, how far the car went, the catapult score, and adjusting its internal policy to generate better designs over time. It's learning from simulated experience.
And the main impact of this RL phase was?
Primarily, it significantly boosted the machine validity rate. That's the percentage of generated designs that could actually be parsed, built without collisions, and met the basic task constraints, like the catapult's 3-meter height minimum. Basically, RL made the agent much better at not producing complete nonsense. It learned the structural rules and physical limits of the sandbox.
Which, in turn, allowed the performance scores to go up.
Yes, because it was exploring the space of working designs more effectively. That's how they gave those big score jumps. The Carmack score going from around 20 to nearly 46, and the Catapult score improving substantially to 7.14 for the best cold start plus RL model. It shows you likely need both. Good initial structured knowledge and targeted reinforcement based on actual simulated physics.
They also looked at the search strategy within that multi-agent loop, comparing things like Monte Carlo tree search, MCTS, against simpler methods. What came out of that?
MCTS generally performed better, especially in terms of how much the average score improved with each refinement step or node expansion. It makes sense because MCTS is a smarter search method. Instead of just randomly trying modifications, it tries to explore branches of the design tree that look more promising based on previous simulations.
So it focuses the refinement effort where it's most likely to yield improvements, rather than getting stuck trying random things in a dead-end part of the design space.
Precisely. In a space this huge and complex, guided search like MCTS is really valuable for efficiency. They also noted that including the edit history, letting the agent see previous attempts and refinements, helped reduce the number of failed attempts needed to get a valid machine, Longer context helps.
Okay, wrapping this up then. What's the big picture here? It feels like we've learned that getting AI to do real engineering design isn't just about scaling up generative models.
Absolutely not. It requires this combination of, 1, a grounded environment with realistic physics, 2, crucially, the right programmatic representation that construction tree was non-negotiable, and 3, an agentic workflow that allows for iterative refinement based on physical feedback, ideally boosted by RL.
You need the AI to reason precisely, physically, and structurally.
And what's really fascinating looking at the resultant failures
Yeah.
is this constant tension between appearance versus performance. Sometimes the LLM would generate a machine that looked incredibly awkward, almost nonsensical to a human eye, but it would perform brilliantly because it perfectly exploited some nuance of the BesiegeField physics.
While a design that looks elegant and intuitive might just collapse instantly.
Exactly. It suggests that current LLMs, even when optimizing for performance, don't necessarily share our human intuition about structural elegance or stability. Their reward functions are still quite narrow: maximize distance, maximize height distance. We might need to figure out how to encode notions of robustness, efficiency, or even aesthetics into the rewards if we want designs that are not just high-performing, but also practical or understandable.
That leads perfectly into a final thought. If LLMs are starting to master compositional design and physics in simulators like BesigeField, what's the next major hurdle to make these AI-generated blueprints truly useful for real-world engineering? You mentioned they abstracted away some complexities.
I think the biggest one is integrating manufacturing constraints and material properties. Right now, the AI designs things, assuming perfect parts and free assembly. The next step is to teach it about cost, material strength, manufacturability, assembly complexity. Can you actually build this thing affordably and reliably with real materials and processes? That means adding those factors into the simulation, into the agent's reasoning, and critically, into the reward function. A catapult that works perfectly but requires impossible materials or costs a fortune isn't a useful design. Bridging that gap between simulated performance and real-world feasibility is the next grand challenge.